Good afternoon, everyone. I'm from Italian Space Agency, and on behalf of the AMS collaboration, I'm going to present the monthly time-dependent fluxes for the proton, helium, carbon, and oxygen in cosmic ray with the AMS on the International Space Station. As we know, the galactic cosmic rays are originated from some galactic sources like supernova remnants, and when they arrive close to the Earth, it's possible, and some observatories like AMS observe them inside the heliosphere, but also the Voyagers, we have local interstellar spectra reported by the Voyagers. So in the interstellar medium and also in the heliosphere, we have measured the cosmic ray fluxes by some experiments and detectors, cosmic ray detectors. So once the galactic cosmic rays arrive in the heliosphere, they have some interaction with the magnetic field and also the solar winds. So these interactions leads significant global and temporal variations in the intensity and their energy as a function of position inside the heliosphere, which is called solar modulation. And since we have a spectra in the before and after entering to the heliosphere, it's possible we have possibility to study the solar modulation. Here for AMS, which AMS start to collect the data from 2011 and is expected to take data during the whole International Space Station lifetime, which is supposed to extend to 2030. And in this period, almost it will cover 2 solar cycles in the different polarities and also in solar maximum and minimum activities. So we will have all the solar activities, and we have enough data to understand better the solar modulation. And AMS, as we know, is a large acceptance high energy magnetic spectrometer, which is able to perform precise measurement of the particles in the range of GeV to TeV. By today, it's almost collected, AMS has collected more than 206 billions of cosmic ray events. I would say roughly in hundreds in per second cosmic ray detected. So here we see some characteristic information of this instrument about this weight and the dimension and the date of the launch. And here this figure shows the subdetectors of the AMS. In this experiment, the particle and nuclei are measured by their charge and momentum and also the energy, or by finding the rigidity, the momentum over charge ratio. And the charge and momentum, I mean the rigidity, can be independently can be measured by different subdetectors by this experiment. So the best way to study the cosmic ray propagation in the heliosphere is the Parker equation. As we see here, this equation has different terms, these different diffusion and drift, solar wind convection, and also the adiabatic energy losses. This term, diffusion and drift, is sensitive to the velocity of the nuclei. So if we have 2 different nuclei with different, the mass to charge ratio, which cause to different velocities, so it's sensitive to that one. And it means that they will have different behavior for their propagation and finally for their intensity and fluxes. However, the last term, adiabatic energy losses term, depends on the spectral shape, which means if 2 nuclei have different spectral shape outside the outside the heliosphere in the interstellar medium, so this term is responsible to explain them, and it will turns out that the fluxes will be different. So finally, we have nuclei with different mass to ratio, which causes the different velocities, and the spectra in the interstellar medium will have different propagation behavior inside the heliosphere. By knowing this and this introduction and knowing, so we start to, I'm going to show the results of the AMS. As we see here, this one, the left panel shows the fluxes of the proton and helium as a function of time. We see from 2011 to 2019 almost data for 8.5 years, which cover the 115 Barter rotations. So each data point here shows the flux for 1 month, or Barter rotation almost 27 days. Here we see the proton and helium have present the time variation, as we see here. You see, so it's not constant as a time, but as we see, the helium has more modulated with to respect to the proton fluxes. To better understanding, we calculated the ratio proton over helium, this ratio, in a selected rigidity beams. We see here, which since proton and helium have different mass to charge ratio, so they have a different velocity and also different spectral shape. So from, but the first reason is more dominant according to the numerical models, and they will have different behaviors in time. Okay, so how about the carbon and oxygen? Carbon and oxygen also here is a, you can see the carbon and oxygen fluxes as a function of time, how they evolved in time. So we see again carbon and oxygen fluxes present, also the time evolution is not a constant, and for their ratio we see it's almost constant with the constant trend here we see. So carbon and oxygen have the same mass to charge ratio, so they have the same velocity. So any time dependence comes from the spectral shape differences in the before entering to the heliosphere. The observations here, so for the carbon and oxygen, since it's constant, this ratio, so it implies that the carbon and oxygen local interstellar medium also have very similar rigidity dependence in the range that the observations has been done. Since carbon and oxygen has the same almost behavior and time evolution, in order to have a more significant better understanding and also the better resolution, here show the helium over carbon plus O and proton over C plus O in red and blue. We see for the proton over C plus O, flux ratio is not compatible with the constant value. If we see here, it has some decreasing behavior trend below 3 GeV. How about, however, for the helium over C plus O, we see the blue line, it has some fluctuations over the constant trend, so it's almost constant. And it seems there is no variation in time for this ratio. So what we can conclude here, proton over carbon and proton over oxygen. So numerical models need to disentangle between the velocity and local interstellar difference. However, for the helium over carbon and helium over oxygen, since they have the very similar velocity, so any time dependence comes from the spectral shape differences in the interstellar medium. Just to conclude, sorry, this talk. Here I put all the data for the proton, helium, carbon, oxygen as for selected rigidities. We see for the higher rigidity is almost flat. All the trend is flat, but because in the lower rigidities are more modulated. So finally, the AMS on the International Space Station is operated since 2011 and also is expected to take data by 2030. And the current measurements on proton, helium, carbon, and oxygen based on the event collected in 8.5 years, which covered the 115 quarter rotation. And the results obtained can give important information regarding the propagation of charged particles inside the heliosphere. So these are the latest results of the AMS, time dependent, for the primary cosmic rays from the AMS.